Can everyone see the whiteboard?
Yes.
Okay, perfect. All right, so I don't have a PowerPoint, so I'm just going to be writing the lecture. And at any time, if you guys have any questions, feel free to stop me. I mean, we have until 7, so if you guys have a question anytime throughout the lecture, just ask. So I'll title this Electron Configuration. And excuse my writing, as you all know, it's not easy to write on this. Configuration. And I'm also going to go over quantum numbers. And when it comes to electron configuration and quantum numbers, they go hand in hand. And as we go on today, we'll see how they relate to one another. Oh my goodness, this is right. Quantum numbers. All right. So from 1A, do you guys remember anything about quantum numbers or anything comes to mind?
Honestly, I don't remember him going over it last semester.
Okay. Right. So with quantum numbers, there are 4 quantum numbers. And on the email that I sent, there's a sheet attached to it. So the 4 quantum numbers that you guys should know for chemistry is the N quantum number, and then this little cursive L, and then M of L, or M sub of L, and M sub of S. So for N, the N stands for the principal quantum number. So principal quantum number. And our N is going to be, and then we'll do examples after I'm done explaining this. So the N is the principal quantum number, and this is associated, and I'm so bad at spelling, you guys, associated with the energy level within that specific atom that you'll be looking at. Level within an atom. Now with our L quantum number is our angular momentum quantum number. So angular momentum quantum number. And on your Chem 101, you guys have questions like this, like, oh, what is the angular momentum of this? And basically what that is, it's associated with your sublevel. And usually that also describes the shape that you're working with. So for instance, so let me finish writing this down. Associated with a sublevel. For example, if we take a look at our S angular momentum quantum number would be 0, right? And then for P, remember your blocks, your electron configurations, you have S, P, what else? So remember you have your electron or your periodic table, right? And we know that this is the S block, and then followed by this element right here as well. And then this block is what? Your transitional metals. What block is that?
D?
Right, your D block. And what about this section? So So you have your S, your D, your P block,
Oh,
right?
F.
Right, and then your F block. So usually when we talk about electron configuration and with quantum numbers, this is usually an indicator of how our electrons are being arranged in our atom. So that's why we do this. Let's see. Yes. So having said that, we have our S will be 0, our P will be 1, SP, and then our D would be what? If we keep moving forward. Would be 2, and then F would be equal to 3. And then we have our M sub of L. And again, this is your magnetic quantum number. Magnetic quantum number. And again, this is associated with the specific orbital within that sublevel. And then we'll do examples. Specific orbitals within the sublevel. And then our M sub of S is our electron spin. Now, our electron spin isn't affected by our other quantum numbers. That thing is on its own. So your electron spin will either be a positive 1/2 or a negative 1/2, depending on how your electron is rearranged when you write down or when you arrange your electrons. So if we go on to an example, we have Is it okay if I erase this, or do you guys want a couple of minutes to write this down?
I'm good.
You're good? Okay. Right. So when it comes to the shapes of our different sublevels, we have the S, we have the P, the D, and the F one. Oh. So for S, whenever we're working with an S orbital, right, it's going to look like a sphere or a circle. This is like a 2D shape. Now our P is going to look like a dumbbell, right? And with this one, it can always be in different axes. It doesn't specifically have to be in one. Sometimes it's in your X, sometimes it's in your Y axis. So for example, you can have a sub or a dumbbell or a P orbital that's on your X axis, and it's going to look like that, P of X. You can also have a P of Y, and it can be located on your Y axis. And you can also have a P of Z, which it's kind of like an imaginary axis right here. So that's how our dumbbell is going to look if it's P of Z. Okay, now as you go further along, they get a little bit more complicated. Your D would look like a 4-leaf clover. And then your F is just super complicated. There's not really a way of like drawing it. But if you were to draw the shape, it would kind of look like this. So you have, and there's many shapes to it. And the notes that I send you have a diagram of all of the shapes that are in each orbital. And then it would look like that. I know it's so bad. So then you have your S, your P, your D, and your F. Okay. So let me draw an example so you guys can see like how we can put everything together. So here, for example, let's say you have a 3p5. And they're asking you to find all the quantum numbers of this specific configuration. So again, we have 4 quantum numbers. We know that we have the N quantum number, L, M sub of L, and then M sub of S. When it comes to seeing which one is associated with each quantum number, this number in the front is going to be our N quantum number. And P will give you the value of L. So this subshell will give you the value of L. So in this case, N is 3. And what would be our L? So remember, S is equal to 0, P is equal to 1, D is equal to 2, and then F is equal to 3. So if we have a P subshell, what would be our angular quantum number? So Mauricio said, yeah, 1. That's correct. Because this is what we're going to use when we're trying to find our angular quantum number. We're going to refer to this. So because P, we have a P right here, it's going to be equal to 1. Okay. And then we have our M sub of L, or another thing to note before I keep going. This tells us how many electrons, so the number of electrons that are present. And also we need to focus on our 5th electron. So there's 5 electrons and we have to focus on our 5th electron, on our last electron. And you'll see what I'm talking about as we go on. So we have M of L. Now our L is 1, but our M of L, that's going to be your range. So meaning it's going to be between negative L to positive L. So here we have a positive 1, or just a 1. So that means that our range is going to be between negative 1 and 1. So it's going to be negative 1, negative 1, 0, and 1. So that's our M of L. That's our range. Those are our subshells. And then our M sub of S, we don't know our M sub of S until we actually rearrange the electrons that we need to arrange. So right here, this kind of tells us how many little subshells we need, this range right here. So we have negative 1, we have 0, we have 1. Another thing to note is Hund's rule. I don't know if any of you are familiar with Hund's rule, but with Hund's rule, usually it just states that whenever you're filling out your electrons, that you make sure that you fill out each subshell with 1 electron first, and then you go on by filling out the other ones. And the reason for this is because electrons, they are kind of like negative people. They don't like sharing a space unless they have to. And also another thing to keep in mind, because they're both negative, they're going to be an opposite spin. So this is a negative and this side is a negative. So that's why we have to draw them the way that they are right now, or the way that I drew them like this. So for this one, how many electrons do we have for this particular configuration? A number, electrons. 5, yep, that's correct, Mauricio. So we have 5 electrons. And again, we know this because right here, this exponent is 5, right? So that's our number of electrons, and that's how many electrons we're going to use. So then, according to Hund's rule, we're going to fill them out. So we have 1 here. Excuse me, you guys. So according to Hund's rule, we need to make sure that, again, we fill out all of the subshell levels first with 1 electron, and then we fill it out with the remaining. So we have a total of 5. So the way we do it is 1, 2, 3, 4, and 5. Now, we have to focus on the last electron that we drew, and it's this one, and it's facing downward. So if it's facing downward, is it a positive or a negative?
Sorry, have a meeting. Mean.
Is it negative?
Right, it's negative. And why is it negative?
Because it's going down.
Right, it's facing downward. So our M of S is going to be negative 1/2. Okay. Does anyone have any questions so far? Okay. All right, so I'll keep moving forward then. So we also have these definitions. So we have paramagnetic, or let me erase this. Is everyone okay? Can I erase this?
Yeah.
Okay. So we have paramagnetic, and we also have diamagnetic. And what this means is that a paramagnetic element are elements with unpaired electrons. And with diamagnetic, di meaning 2, they are completely paired elements. So if we take a look at the previous question that we did, so we had this. Would you say that this is a paramagnetic element or a diamagnetic element, and why? So remember, paramagnetic are elements with unpaired electrons, and diamagnetic completely paired. All the electrons are completely paired with each other. So is this a paramagnetic or a diamagnetic element?
Paramagnetic.
Right, paramagnetic, yeah, because you have this electron that is not being shared with another one. Okay, so I'm gonna do another one, but I want you guys to do it as a group. So let's say you're given this on a test. Let's say that you have to find the quantum number of 4d4. So what is our N? What is our L? Our M of L? Our M of S? So who wants to start it off? All right, Mauricio, go ahead. You can start. And, right, N is equal to 4, right? So what about our L? What would be our L equal to, and how do we know what our L is? Right, our L is 2. And the reason being is because why? Why is our L 2? How do we find our
Don't
L?
you because you divide it
So not
or maybe
exactly.
multiply it?
So not exactly. So remember we said our L is our angular momentum, right? It's our sublevel.
Yes.
And we have an S, P, D, and F, right? And if we have an S sublevel, our S is going to be 0. If we have a P, it's going to be 1, a D 2, and then
2.
an F 3. Right.
Mhm.
So if we take a look at D, it gives us a 2, right?
Yes.
So then, yeah, therefore it's 2. So what about our M sub of L? What would that be? How do we know how to find that? So it's kind of that's going to be your range. Remember, from negative L to positive L. So in this case, you have a 2, meaning that your range is going to be from negative 2 to positive 2. So negative 2, negative 1, 0, 1, 2. And then our M of S, we don't know. We're not going to find out until we actually draw it out. So here we know that we have our M sub of L is from negative 2 to 2. So let's do that. So we have negative 2, negative 1, 0, 1, we have in this case. So how do we know how many electrons we have?
Isn't it 4?
Right, 4 electrons, correct. Because of that exponent. So then according to Hund's rule, right, we're going to make sure that we spread them out. So we're going to do 1, 2, 3, 4. Now, let me do one where you don't follow Hund's rule. It's going to look like this: 1, 2, 3, 4. That means that these electrons are all paired up, right? But that you still have all of these spaces. And the first, or option A right here, letter A, is incorrect. And if you have something on a test like, oh, which one follows Hund's rule, you got to make sure that when you draw it out, that each electron gets paired in, or each electron gets drawn into one of the subshell, and then you can draw the other ones. So even though this is 4 electrons, this is incorrect because it doesn't follow Hund's rules. And then therefore your spin is going to be wrong, because right here we have an electron that's facing down, therefore your spin would be a negative 1/2. But if we take a look at the one that we did following Hund's rule, we have an electron right here. That was our last electron, and it's facing up, and therefore it's a positive 1/2. So that's why it's really important when you fill these out that you follow Hund's rule. Any questions on this one?
Hi, imagine in the test, I'm not gonna even know like how to follow the hamster's rule. What's the name of the guy?
Hund's?
Oh, Hans.
Yeah.
Do you think like we can do another one of these so that way we can practice a little bit more?
Yeah.
Yeah, because I get confused with the part over here, you know, the little arrows going up and then the other one's going down.
Mm-hmm. Okay. Yeah, we can do another one. So think of electrons like introverts. They don't like talking to people. They don't like being with people. They like being in their own room. But they'll share a room, or they will share a space if they have to. So that's why we draw them out first, like how we did here for B. because this would be incorrect, but let's do another one. So let's say we have 5F13. All right, so what would be our N? What would be our L? Well, our M of L and then our M of S.
Your N wouldn't be 5.
Right, your N would be 5.
Mm.
If you want, you can draw on the board.
Let me see. 5 divided by. And then for L, oh my goodness, it wouldn't be, no, let me see. I don't know if I'm wrong. Let me see. It wouldn't be 3, right?
It would be 3. Why would it be 3?
That's the thing. That's the equation I'm asking myself.
So remember, we have the angular momentum, which is your L.
Yes.
And remember, we said that if you have an S sublevel, it's going to be 0.
Mm-hmm.
If you have a P, it's going to be what?
1.
1. If you have
And then D equals 2.
right?
And that would be 3.
Right. So that's why this is 3. Because right here you have an F.
It's because, you know, I was dividing 5 and 13.
Oh, no, don't do that. That would be not
It's
correct.
because I was dividing 5 and 13. So at the end it was 2.6. So 6 is big. So it goes rounds to 2 and then 3. So that's...
No, I see. Yeah, no, that's too much. That's too much. That's not necessary. So whenever you want to figure out your angular momentum, which is your L, you take a look at what sublevel you have.
Mm-hmm.
So if you have an S, your L is 0. If you have a P, your L is 1, and so on and so forth.
Mm-hmm.
Okay.
Mm-hmm.
All right. Now your M of L, remember, I keep saying it's positive L to negative L. So in this case, what would be your range? So if we take a look at our L is 3, right? And our M sub of L is going to give us that range of our L. So what would it be? So let's say our L was equal to -2, or not 2, that's never going to happen. Our L is equal to 2. Our M sub of L is going to be between positive L or negative L to positive L. So we take a look at our L and it's 2. So it's going to be our M sub of L is going to be -2, -1, 0, 1, and 2. So having said that, where would be our M sub of L for this case if we have an L of 3? Any volunteers? So it would be our range. Oh, yes, Mauricio, you're correct. It'll be from -3 to 3. So it's going to be, yeah, -3, -2, -1, 0, 1, 2, and 3. So then let's do that. We have -3, -2, -1, 0, 1, 2, 3. And for this one, how many electrons do we have? How many electrons are we working with?
Don't we have 13?
Right, we have 13 electrons. So remember, according to Hund's rule, we want to make sure that we fill out each sublevel first with 1 electron because electrons are negative. They don't like sharing a space. And then from then on, if we have remaining electrons, we will fill out the other rooms with them. So here there's 13 electrons. So we do 1, 2, 3, 4, 5, 6, 7, 7, but we have 13. So we'll set the other one, 7, 8, 9, 10, 11, 12, 13. So that means that we take a look at our last electron right here, and it's facing downward. So if it's facing downward, our M sub of S would be what? So remember, if you have something that's facing downward, it's going, your M sub of S, or your electron spin, is going to be -1/2. But if it's facing upward, it's going to be +1/2. So in this case, it's facing downward, so it's going to be, and don't be scared, you guys, to participate. We're all learning here, so be confident. Even if you think you're not correct, be confident. We're all learning. It's okay to be wrong. It's better to be wrong right now than on the test. So in this case, our angular momentum, or our M sub of S, would be what? Positive or negative?
Negative?
Right, -1/2. And your M sub of S is always going to include that half. I don't know why. I don't know the science behind why that the half is there. But what I do know is that if it's facing up, it's going to be positive. If it's facing down, it's going to be negative. Do you guys want to do one more just for practice? Oh, yes, Mauricio, I saw your answer. Do you guys want to do another one? All right, so let's do, okay, so actually, so how does this relate to our electron configuration? So let's take one of the elements. Let's take phosphorus, for example. So we have phosphorus. We know that phosphorus is P, right? Or it kind of looks like this. So 31, 15. Now, if they're asking you to find the quantum number of phosphorus, or write down how the electrons are going to be paired up. So if we take a look at phosphorus, do you guys remember how to do electron configuration from 1A? Where you had to go from different blocks. Remember, we have our S, we have our D, we have our P, and we have our F. And we had to count off like 1s2, 2s2, so on and so forth. So with this, if we take the electron configuration of phosphorus, we know that, first of all, we know that phosphorus has 15 electrons because our protons are equal to, remember, our protons are equal to electrons, except when you have an ion, right? But in this case, we don't have an ion right now. We have an element in its ground state. So we have 15 protons, therefore we have 15 electrons. So our electron configuration for phosphorus would look like this: 1s2, 2s2, 2p6, 3s2, and 3p3. Okay. Does anyone have any questions about how I got this electron configuration right here? Or can I move on? All right. So basically, what we want to do, we want to make sure that we arrange our electrons correctly. So the way that we do this, we have our 1s subshell, 1s, and then we have our 2s subshell, and then our 2p. And remember, p has 3 different levels, 3 like this, 1, 2, 3. So that would be our 2p. And then our 3s, and then we have our 3p. So 1, 2, 3. And remember, each level can hold up. Oh, okay, Mauricio. So when it comes to our electron configuration, let me see if I can pull out an periodic table. Okay, so we have our periodic table of elements. And just to, for recap, we have So to find the electron configuration of something, remember we have our blocks. So this is our S block. We said this is our D block. And then helium is that lonesome element, and this one is actually part of the S block. And then here we have our D block. And then way at the bottom right here, we have our F block, except for these 2 elements, which are part of your D block. So if we were trying to find the electron configuration of phosphorus, which is right here, remember these are levels 1, 2, 3, 4, 5, 6, 7. And then it gets a little weird when you get into your D block, because instead of starting at the 4th level, it's going to start at that 3 level. Remember 3D1, 3D2, so on and so forth. So here, if we want to find the electron configuration of phosphorus, we start off with our 1s1. Remember 1 being that first row, S being that S block, and 1 being that first element or that first electron in that block. And then we have helium, which is, again, our first row, and it's still the S block, but it's our second one. And then we go on to the second row. So 2s1, 2 being the second row, S being the second block, and then 1 being that first one on that second row in that S block. And then we do the same thing with beryllium, 2s2, and then we're going to skip on to our P block. And because we are in our second row, we're going to start off with 2. And we're in our P block now, so it's 2p1, and then 2p2, 2p3, so on and so forth, 2p6 with the M. So that's how you get the electron configuration of elements in your periodic table. So here we were working with our phosphorus. So if we were to do that with phosphorus, if we were to do what I just showed you right now, the electron configuration of phosphorus would be this. And we said earlier that this just tells us how many electrons are in that subshell level. So in 1s2, there's 2, and that works out perfectly, because the way that this is like a really bad drawing, but usually the way that the levels are drawn, you can actually kind of see as they increase. So for instance, let's see if I can do a better drawing. So the thing with the electrons, the atom, they always want to make sure they fill up all the orbitals that they have and that they're arranged in a specific way. So for this one, we have, so 1s would be like right here, and then 2s up here. And then you would have something like this. So 2p slightly up. And then you would have 3s again here. Right here. And then you would have slightly up 3p. So this is how the levels would look like when you're trying to rearrange the electrons within the electron configuration. So if we take a look at 1s for phosphorus right here, we need to make sure that we fill out that first level first. And we have to do it according to Hund's rule. But because it's just that 1s, we fill it up first. So 1, 2. Then we go on to our next level, which is 2s2. And again, it can hold up to 2 electrons, right? So we go 1, 2. Now, our next one is 2p6. So again, according to Hund's rule, 1, 2, 3, 4, 5, 6. And then we would go to 3s2, and again 1, 2, and then 3p3. So 1, 2, 3. So this is how it would look like for phosphorus. And again, that's why you guys can see how everything kind of like goes with each other. You have, the electron configuration and then like quantum number. So if the quantum number for this one, let's say you have 3p3, right? We said N, L, M sub of L, right? And then we have M sub of S. And usually they'll ask you for a specific configuration when they're asking you for quantum numbers. So in this case, let's say they ask you for 3p3. We can go back to what we drew, right? And we're like, oh, well, this is 3p3. But our N would be what again? What would be our N? Three, right? That's correct, Mauricio. 3. So yeah, 3. And then we said our L would be what for this specific configuration? How would we know our angular momentum?
Three? No way. Yeah?
Not exactly. So Mauricio on the chat said 1. So remember when we want to find our L or our angular momentum, we have our S is equal to 0, our P is equal to 1, D is equal to 2, and then F is equal to 3. So in this case, right, we have our P. So therefore our angular momentum, our L is going to be equal to 1. Okay. So then what is our M sub of L if that's the case? So it's going to be between -1 and 1, right? Because our L was 1. So we have our M sub of L is -1, 0, and 1. Now, what is our spin? Is it going to be positive or is it going to be negative? And again, you guys don't be scared to participate. I'm not going to be like, oh my gosh, how dare you? Like, we're learning here. It's fine. So it would be our M of S. Positive or negative?
Negative, because it was 1/2, I remember, in the other one.
Right, you're correct. And also Mauricio, yeah, both of you are correct. So it's negative 1/2 because remember our configuration right here, we need to focus on that third electron. So if we actually, if we take a look at our third electron, it's facing what way? So we have negative 1, 0, and 1, right? So we have negative 1, 0, and 1. And we have to abide by Hund's rule. So 1, 2, 3. This is our last electron that we put there. And it's facing upward. Therefore, it's going to be a positive 1/2 for our electron spin. Okay. Do you guys have any specific questions on what we have been going over? Don't be afraid to ask questions. That's why you're here, to learn. Are you guys familiar with cations, anions, isoelectronic, all of that stuff? Do you guys remember that? Okay. So let's do, just for a recap, let's go over that. So let's say I have something like this. We have Se to negative. So this element is not in its ground state because it's giving us a charge. Therefore, what is this? It's a cation or a anion? Right, Mauricio, you're correct. It's an anion. Anion. It's so hard for me to say. Anion. And remember, anions are negative and cations, we said, are positive. Now, if we want to find the electron configuration of this anion, the first thing that you always want to do is, or at least this is what I do, I always write the element or the element that's associated right here and its ground state, meaning with no charges involved, as if this didn't exist, this too. So if we were to actually find the electron configuration of Se, so if we take a look at our periodic table, we would do 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then we have 4p4. Right? So this is in its ground state without the ions. So now with this 2 negative, what's happening? Are we taking away electrons or are we adding electrons? What's going on with the electrons with this ion? So we are adding electrons, right? So we always want to go to the highest level. So in this case, it would be our 4p4. So we know that our p sublevel can hold up to 6 electrons, right? And because of that, we can actually add them here. So our new electron configuration for this specific anion, so if we were to do the anion, would be 4p6. Right. So any questions on this? Right. So that's all I was gonna go over tonight. But if you guys have any questions, feel free to ask. Mauricio. So Mauricio asked why add the 2 electrons. So remember, Mauricio, we have 2 negative right here. And we have an anion, like you said. So here, remember, electrons are negative. So if you add 2 more electrons, right? So let's say you have 4 negative people, like this. But if you had 2 more, there's 2, and then you're gonna add 2 more negative people, there's gonna be a total of 6. So let's say you had a 2 plus here. That means out of those original 4 people that you had, 1, 2, 3, 4, 2 of them are now going to be happy. So that means that you're going to take away those 2 people, and then you're going to be left with this. So the reason that we add those 2 electrons is because it's an anion, it's a negative. We're adding electrons. And when it comes to electron configuration, we're always going to be working with electrons, not with protons or neutrons when it comes to electron configuration. Does that make sense? I see. Okay. Yeah, we're working with electrons here. Right. So any more questions? I see. Yeah. That happens sometimes. You ask a question and then you're like, oh wait, you answer your own question sometimes. Right. So anyone else have any questions regarding anything that we went over tonight? And feel free to ask. Don't be scared. All right. All right, then I mean, if you guys don't have any more questions, I am done with my lecture.
Is there gonna be class on Monday?
Yes, there will be class on Monday.
Are we gonna have a lab as well or no? Not yet.
To be honest, I'm not sure. That's something that Dr. Henry should email you guys, or you should email Dr. Henry asking. Because all of you, I think, got your lab kits, right?
Yes.
Okay. So maybe he'll be starting or maybe not. But if not, I can ask and then I can just send an email. Yeah.
Okay.
Yeah. Right. Any other questions? All right. So some of this stuff is in your Chem 101. So whenever you guys want to, like if you guys want to do your Chem 101, I also have tutoring. So feel free to join tutoring hours as well. But other than that, you guys are all free to go. And thank you for listening to my lecture. I hope that this made sense. Have a good night, you guys.